go. Where am I? Here am I? Okay. Let's start. Today I would like to speak on Harmonics thematic on the voltage quality and harmonic components in relation to the power networks. Yeah, ready. I have a small demo here. This small generator. It has excited system on magnets and the rotor. I can plug it in. Let's see. Yeah, you can see it's generate some electricity. But what will scope show us? Here it is. Look at the voltage. It's a problem of small generators. They do not produce a sign like voltage what it should be. Where the dog is digging. Here, I have a spare rotor. Okay. It's something like this, something round. If we have rotation with the frequency omega, this is one way for magnetic induction, and this is the second one. If we draw a chart, this is angle of, we will see what we will see. Something like this. Pole N. Chart of induction will be something, okay, something like this. To get a sign voltage, we need this line to be cosine, because induced voltage is minus number of turns and flux derivative. To have sign here, we need to have flux and induction cosine. This is not cosine. We have this generator produces something disturbed. It is common problem for designers of generator. There are different ways of solution. For example, it's a winding. Look at this rotor. You can see it's like a gun barrel. The cuts are not straight, but form a kind of helix or spiral. That's how designers made voltage more close to sine. Very common measure, for example, on the larger generators with structure like this, or cut this area to make magnetic resistance in this path high. Or, very popular, is to reduce amount of steel by cutting kind of channel or replacing part of steel with non-magnetic material like micat or something like this to reduce magnetic conductivity in these areas. I don't know, can you see? This one, maybe from this side is better. This small generator has a system of 4 poles, but without, second I will connect it, without proper pole alignment. Proper shaping of the pole, it produces voltage like this. It's a help. Larger generators, of course, produce more voltage. But anyway, any real generator do not produce ideal sign. Any real generator, let's say, has a difference from ideal cosine in the magnetic flux distribution curve. This meaning what any voltage of any real generator contains some disturbances, some harmonics. Now I would like to show another generator. This one simple from the traditional physics. Can you see the rotor? I have one demo generator. This one. It's a demo. I have a steel ring. Inside I can place small magnets on my wheel. I can place, here it is, ring. I can place magnets as I want. 1, 2, 3. Oh, here I have 4. Set of 4 magnets, and with the help of this belt I can rotate it. Let's take a look on the voltage. One moment. I'll connect it. 1, 2, 3, 4. All magnets here. 1 second. This wire is wrong. This one is attachment in the box. And here. Okay. I have circle. I have rotating link. I will place 2 magnets like this. This will be south, north, and north, south. I'll place 2 magnets. I'll place 2 magnets. I'll place 2. This one and this one. Here it is. Here is my voltage. Frequency determined by, I can make it visible. So rotation frequency is determined by my force, and voltage distribution we see. Now, question: what will happen if I put another magnet here, for example? I'm adding 1 more magnet here. Do you see what happened? I had still symmetrical curve, but it contains 2, 1, 2, 1. You see what happened? I remove this additional magnet. symmetrical curve with equal periods. I'm adding to 1 to 1. I can make something like this. I have put here very near additional magnet. They are very close. And you see what happened with these two waves. See what happened with voltage curve. Here it is. 1 and 2 magnets near. Here they are. What kind of conclusion can we make from this experiment? We should make some conclusion. And our conclusion is what we saw. 1, 2, period, another 1. What the voltage wave or angular shift is determined by the design of magnetic system. If we speak, for example, free-phase machine, this will be A phase, B, C. 2/3 of P. In such design, we will have shifts by 2/3 of P, 120 degrees. If we have I will switch to my board. Shift between lines of the coils of the winding, we will have the same shift when we speak on voltage. But what if we will order, okay, I can order, let's say, 150 degrees, 150 degrees, and 60. What will be phase shift? 150, 150, and 60. Phase shift of the voltage is determined by design of the magnetic system. Now we have induction and flux distribution, not cosine, something. Meaning what voltage will have not only sine component but higher harmonics. Let's say phase voltage. It will be first harmonic sine omega t plus. Can it have second harmonic? No. In stationary regime, no, only during the transients. Why? Because we have a symmetry here. After half a period, rotor turns, so we have a symmetry, meaning what? There will be no second, fourth, eighth, and so on odd harmonics. On the rectifier network, if we speak on power, can have 100 Hz component. Okay, if you have a base of 50. So, I'm already writing 3 sine 3 omega t. Okay, plus some. There should be some 3. Okay, let's. Fifth harmonic sine 5 omega plus something 5. It's not important. What important? Let's say 50 Hertz. 1 omega t. A phase. 1 sine omega t. Will be the same 1 sine omega 2/3 of p. And the phase will have sine omega plus 2/3 p. Nice. Star 2/3 of p. Nice start from the book Basics of Electrotechnics. Rotate it this way with the frequency omega being 50 Hertz. Okay. It's fine. But what about third? A phase will be some mod sine 3 omega t. For simplicity, I will say 3, 0. It's just for simplicity. At the phase B, we will have sine of triple omega minus 2/3 of p. Triple frequency, and this angle is determined by design of magnetic system. But it's equal to sine 3 omega t. Because full circle to periods change nothing. Good? Now see will be sine triple omega plus 2/3 or equals triple omega. Ho! We see a quite different picture. For the third harmonic, we see all three voltages collinear in one direction. All three voltages are directed the same way. It's unusual. Now let's see what will happen at omega t. In Europe it will be 200 Hz component. Will be some max voltage sine 5 omega t. I'll set Fs0 for simplicity. But what I need to write 5 here will be sine 5 omega minus 2/3 of t, and it's equal sine of 5 omega. And what we will have here? 10/3 of p. What it will give us? We can omit 2p already. And what we will have? 10/3. It's 3 1/3 or same 1 1/3 of p. Full rotation 1. Wait 1 second. We were here. Full rotation of p will bring us there. Plus 1/3 will bring us here, and it's relative to this vector is nothing else than 2/3 of p. Plus whoa. The same for C phase, being sine 5 omega plus 2/3 p equals to 5 sine of 5 omega t minus 2/3 of p. For 5 omegas, we have A, C, B system. symmetrical three-phase system, but with the opposite phase sequence. If we continue it this way, we will see some table like this. 1 omega t, 50 Hertz. Normal A, B, C sequence. 3 omega t, 150 Hertz. A, B, C. 5 omega t. Star A, C, B. 250 Hertz. 7 omegas. Again, nice A, B, C star. And let's say 9 omega t, 450 Hertz. A, B, C. All vectors in one direction. If you remember theory of three-phase or polyphase network, there was a technique or method of Fortescue transformation or symmetrical components, when each and every non-symmetrical polyphase network was represented only any linear polyphase network can be represented as a sum of direct, reverse, and zero sequence. So here we have direct sequence, zero sequence, reverse sequence, again direct sequence, and again zero sequence in the terms of Fortescue transformation. Third, harmonics at 9, 15 and so on are behaving like a zero sequence. Fifth, similar, reverse sequence. Symmetrical polyphase, in our case three-phase system, but with opposite phase sequence. If 50 Hertz rotates some machine forward, some engine motor 250, slows it down, produce a moment of opposite direction. Moment of opposite directions. What I like to do, I will show a small demo, let's say small model of distribution network. Let's say we have something like this. 10 kilovolt transform network, city distribution network, delta connection, Earth star at a 0.4 kilovolt network, and some load here. I will simulate it with the help this transformer delta Y will after the distribution I will power it from 220 volts. It will be ground. It's A, B, C phase. Okay, I'll put a current sensor here. And this will be our yellow signal. As a load, I will use old and ineffective incandescent lamps. In the neutral, I will put 1 ohm resistor, and this voltage will be our second signal. Where am I? 1 ohm resistor and current transformer. Wires. More wires for the gut of wires. A phase, B phase, C. A phase, B, and D phase, C phase. Small interconnecting wire, and out. Okay. Yes. Connected. Power. Very well. Okay. It's okay. Yeah, I can switch. I can switch to my experiment. What we got here? Load for A phase, load for B, and load for C. I'm switching power. We have A phase current. Looks like a sine. And this line is a current of the neutral. How can we check what it's working? What will happen if I disconnect one of the phase? Let's say I cut B phase. What will happen? The neutral current will be vectorial. Sum of the A and C. In the symmetrical regime, current was 0. Sum of A and C A, B, C. If I cut B, I need to. It will be. Oh, I can say to the without any question, what sum of A and C equals to minus B when all loads A equals to B equals to C, when all loads are equal. Let's check. No B phase. I have disconnected the B phase. And we see neutral current. Here it is, I can see the offset. Okay, I can bring it back and remove the C phase. Here it is, minus C. What do we see? Phase current assigned and neutral current in symmetrical regime is 0. Unplug them. Now it's time for second stage of our experiment. Let's replace old and ineffective incandescent lamp with LED. One second. I need this one. Oh. You see, current much smaller. This one truly effective. But what's the shape of this current? It's an A phase. We see not only BTB, the red line is a spectrum of the yellow line of the A phase current. Take a look. We have 50 Hertz component. We have third. Oh, come on. 150 Hertz component. Yeah. 250 Hertz, fifth harmonic. We have all it's not very well seen, but it is third, fifth, seventh, ninth harmonics. All the spectrums here. And now, what about neutral current? I have enlarged it. This is current of the neutral in the symmetrical regime. 1 second. I will switch off B and C phase. C it's equal to now to A phase because it's the same current. I have switched off B and C phase. The same current. Now I'm returning. Here they are, all three. A, B, C. All three phases. And take a look on the neutral current. Here is spectrum. I have switched Fourier. Analyze. Maybe I will enlarge it. larger spectrum. To compare, case spectrum of the A phase, first, third, fifth harmonic, and case spectrum of the neutral. What's this? 150 Hertz. Next one. $459 omega t. This one. $750. See what happened? Here was the first harmonic. They are a little bit different. For the neutral, we see a sum, vectorial sum on each frequency. At the 50 Hz for the first harmonic, sum is 0. For the fifth harmonic, for 250, for let's say reverse sequence, sum is 0. For third harmonic, for 150 Hz, sum is triple. For the 50 Hz, I have sum of this A, B, C, A plus B and plus C equals to 0. For 250 Hz, I have A, C, B, sum is 0. But for third harmonic, for 3 omega, for 150 Hz, I have 1, 2, 3. Sum of this means equals to triple. So in modern reality, current of the neutral is not 0 in symmetric regime, but it's triple, 0 sequence, or in our case, triple current of the third, it's contained third, ninth, and so on harmonics. Time changed. When load consumes non-sine current, the electrotechnics law are still in force. But you need to understand something from the theory of signal, because this is reality. This is our reality. Not 0, but triple current of the third harmonics. I'll return good old time. Good all time symmetrical load. Small amount of third. What is it? One second. What I got here? Yes, very small amount of third harmony. Because of transformer. Good old time. And our reality. So for modern network, we often need to consider not only flow of the 50 Hz base harmonic component, but flow of higher components, and we need to understand the effect of it. Additional losses, electromagnetic disturbances, and what else? It's important for higher harmonic components where the dog is digging. They don't have an instant effect on equipment, appears, but they cause a very rapid degradation of insulation in distribution networks. It's not so important for low voltage, but at 10 or 24 kilovolts, it's very important factor of cable structure degradation. And transformer insulation suffers too. When we concern, mostly it's some metal processing industry or chemical industry where the high power inverters are employed. Often infrastructure degradation is connected with high frequency components of the in currents and voltages. For real serious metallurgical plants, often special active filters are necessary, and huge 7 or even 8-digit investments are made to prevent this voltage disturbance. Okay, I think it's enough for today. The key moment is idea. What some harmonic components, let's say, rotates directly, some are symmetrical in phase, but works in they, let's say, has a opposite phase sequence, or let's say, in this frequency, magnetic field rotates in machine, rotates in opposite direction. And some are zero, are acting like a zero sequence, so they are equal in all phase. And it's important to remember.